So, in recent times I've been experimenting with some other components that I find to be very useful. This one is an incrementer. You see how fast it increments too. And so this can be used for components that only need to increment, and they can increment a lot faster than a regular adder cell. This here is the carry out for doing increments on large numbers using arbitrary precision arithmetic, and also for detecting overflow, because both of those things are useful. Over here, however, is sort of a ROM adder where it has a 4-bit input and a 3-bit output, and instead of actually calculating the addition the normal way, it just has a truth table for what outputs correlate to what inputs. And you could probably stack these on top of each other to make a larger bit width version of this, but segmented, so that only portions of it are ROM like this, and the carry over would probably come from this here and go into here. And so the higher points in the stack would have 3 inputs in this case, which is weird. I'm not sure how useful that would be. Over here are the components for the processor that I'm still working on. I had to do a lot of experimentation and invention in order to find a way to get all of these to work very well. And so we still have the regular ALU, but this time I'm going to demo this with a smaller register bank, because this should be easier and faster to use to begin with, just to make sure everything functions correctly. Over here, this is where the counter is going to be. This is a prototype counter I made earlier, and I really don't like how it works. So as you can see, not only does it increment really slowly and not very reliably, as you can see, it's also really big and unnecessarily complicated, because this is actually an adder cell, and over here is a bank of registers. And so if I get the counter working faster, I should be able to actually execute everything faster. The bottleneck in the system is where the clock limit is going to need to be accounted for in. Right now, I'm using these 2 registers for input into the control unit from the data bus. One of them, the first one here, is supposed to take the instruction, and the second one here is supposed to take the argument for the instruction, which is usually an address. And over here is where the output of all of this leads to. Planning on having this part here be the control line going to mainly the ALU, feeding it its native instructions along 4 bits, and the other 4 bits are actually going to be parts of these opcodes here that are not going to be related to the ALU at all. And over here is the output for accessing the register addresses for right now. And back here is actually the sequencer. So I just copied the design for the sequencer I made earlier over to here and refined it to work better in this environment. And as you can see, it has 3 states, and each time it changes a state, it outputs that state to the correlating pin. And I also have it so that it can be reset. And it's directly attached to this clock here. And I'm pretty sure that's everything for right now. It's taken a lot of work to figure out a way to get this component functioning correctly. And I'm pretty sure I'm only about 80 to 70% done with this component alone. And putting all of these together should be pretty simple though. Right now, I have no idea how I'm going to implement I/O for the processor though. What I'm actually planning on, or prefer to have happen, is so that there are actually a bank of addressable registers like that one. Uh, Actually, two of them. One of them for in and the other for out. The in registers will be writable from outside, but only readable from inside, so it would act like a ROM that can be changed from the outside. And then the other half are going to be like this, but uh, actually almost exactly like regular registers that can be read from or written to from inside, or probably not read from because it's an out port, but they can be accessed from the outside, and so it's like the reverse of the in registers, and so it would act like an I/O buffer, which is actually, I'm pretty sure that's how most processors do their I/Os, with I/O buffers that are addressable like regular memory. Although I think I remember most processors' instruction sets having the I/O buffers being handled separately from general purpose memory for some reason, even though it probably just mostly complicates the actual architecture and code for how the processor should work. Now, I'm trying to use a minimalistic instruction set where most of the instructions are as general purpose as possible and universally applicable as possible. Wait, I think I just said that's all to show for now, just a few minutes ago. Well, I did show everything, but there was more to say, but never mind. That's enough for now.